I will not be wasting your time by telling you why we have taken a very simple case of unity feedback system. You can check it out in the previous lecture. For the shown block diagram with open loop transfer function GS, we will have transfer function to be equal to omega square divided by s square plus 2 zeta omega n s plus square of omega n. This form is very important, which is referred as standard form of second order control systems. But if you observe carefully, you will realize that there are no zeros present in this standard form. However, as an undergraduate student, you are supposed to know about how to solve strictly proper transfer functions, but that also gives two possibilities which you see on the screen. Initially, we are going to focus only on the standard form, and laterwards we will see and explore the second form. One important point you have to keep in mind always is that while analyzing the standard form, we will come up with many formulas and most of them are invalid for the second form. Students in hurry directly put the formulas without even checking the form of second order control system and commit silly mistakes. I am just making you aware of silly mistakes you guys generally commit. Look carefully at the form of transfer function before applying any formula. Now, let us first analyze standard form of second order control systems. The zeta is referred as damping ratio and omega n is called as natural frequency. By using the quadratic roots formula, we can simply find the roots of the characteristic equation, which are simply the poles of the closed loop transfer function of this block diagram. You will get the poles to be equal to minus zeta omega n plus minus omega n under root of zeta square minus 1. Now, after a simple manipulation in the under root term, we can introduce j, which is imaginary complex number iota. The location of poles is very important in determining the major parameters in the type of response the system will provide, and as can be observed easily, the value of the poles is dependent upon the value of the zeta. Depending upon the value of zeta itself, there are 4 cases which you have to remember. The first case is when the value of the zeta is equal to 0. In this case, when zeta is equal to 0, the value of the two poles will come out to be equal to plus minus j omega n, which are purely imaginary roots. And if we have to locate these poles on the S-plane, then they will lie exactly on the imaginary axis. If you recall the concept which we have studied in the first unit, then you can also determine that such type of systems are marginally stable. The unit step response for this case will look like this. The unit step response in this case does not contain any damping. That's why this case is also referred as a case of undamped oscillations. The second case is when the value of the zeta is greater than 0 and smaller than 1. In this case, the poles will be complex conjugate roots which is having negative real part. Negative real part has lot of importance. We have already seen in the first unit that if and only if all the poles lie on the left hand side of the imaginary axis, then only the system is said to be stable. Otherwise, it is an unstable system. Now, if you try to locate the position of poles in the S-plane, then they will lie on the left hand side of the imaginary axis. The red dashed circle which you see on the S-plane represents the locus of the poles at different values of zeta. You might be aware of the general equation of a circle, which is in the form of x square plus y square equal to the square of the radius of the circle. If you put the value of x and y coordinate in this equation, you can find the value of radius, which will come out to be equal to natural frequency. We can also find the angle between the real axis and the straight line joining the pole and origin. Also, we know the value of cos theta is equal to base upon hypotenuse. In this case, the base is zeta into natural frequency. Here, we are not taking negative sign because the angle is taken from the negative real axis, not the positive real axis. That's why we have kept the value zeta into natural frequency rather than minus zeta into natural frequency. And the value of hypotenuse can easily be found by putting the value of x and y coordinate, squaring them both, and finally taking the square root of the sum of the squares of x and y coordinate. After solving, you will get cos theta equal to zeta, and as such, we can find the value of theta, which will come out to be equal to cos inverse of zeta. The magnitude of x and y coordinate is also having specific names, like the magnitude of x coordinate which is zeta into omega n is referred as damping factor, whereas the magnitude of y coordinate, which is natural frequency omega n multiplied by under root of 1 minus zeta square, is referred as damped frequency. Don't get confused with damping ratio and damping factor. Zeta is simply referred as damping ratio, whereas zeta multiplied by omega n is referred as damping factor. The same way, damped frequency and natural frequency are different parameters. The unit step response in this case will look like this. You can see there are oscillations, but their magnitude decreases continuously. This is referred as damping, which in simple terms can be defined as the decay of oscillations. This case is referred as the case of underdamped oscillations. The third case is when the value of zeta is equal to 1. In this case, we will be having repeated poles, meaning that the roots will be purely real, equal, and have negative values. In this case, the poles will lie on the real axis. The approximate unit step response will look like this, which does not have any oscillations at all. This case is referred as the case of critically damped oscillations. The fourth case is when the value of zeta is greater than 1. In this case, the value of the poles will have negative real values which are unequal in magnitude. Observe carefully, in the under root term, the original expression was consisting of iota j, and in the under root term, the expression was 1 minus eta square. But the roots in this case does not have iota, also the under root term is slightly changed. This simply happened because we have taken minus 1 from the under root term out of the expression and had multiplied it with iota. Now, in this case also, the poles will lie exactly on the real axis. The most desirable case is actually the second case when the value of zeta is greater than 0 and smaller than 1. As you will see later that there are so many performance parameters for the case 2 that it is easy to maintain and regulate its output values. The unit step response in this case also does not have any oscillations. This case is particularly referred as the case of overdamped oscillations. So, we have seen the 4 cases, what are their general names and what are the general locations of their poles in the S-plane. These cases are very important and you have to learn these cases with their names. Also, the first case is marginally stable as the poles were lying exactly on the imaginary axis, whereas in all other cases the system will be stable. But can you prove any of these cases that the system will be stable? As an example, try to solve the fourth case and determine how you can say that the system will always be stable in this case. You have to use a little bit of mathematics and logical reasoning that if any pole lies on the right hand side of the S-plane, then it will be unstable. For that, we have to check both the values of the poles for the fourth case, which is having higher possibility to reach 0 or even cross the imaginary axis, which is obviously the second pole S2. Obviously, for having positive real pole, the value of this expression should be greater than 0. And after solving this inequality, you will come up with the final expression, which is under root of zeta square minus 1 should be greater than zeta for the system to have a positive real root. But this is not possible. There is no such value of zeta greater than 1 for which this expression will hold true. That's why the poles in the fourth case also are stable.